Hi, Chem students. Let's talk about the mole and molecular mass. It's an opportunity for us to talk about how, by measuring the mass, we essentially can find out how many of a particular particle we have, whether it be an atom, an ion, a molecule, doesn't matter. So when we think about counting, normally we just think about the number of particles that there are, but in chemistry, there's two ways that we can really talk about it. And they're just different scales, but they represent the same thing. So don't get confused by this. So we can talk about the actual number of ions or molecules, whatever we're talking about. However, that number is going to be ridiculously large. And as humans, we feel a little more comfortable if we have, let's say, numbers of a normal size, 5, 10, 100, things like that, 0.5. Those are numbers we're used to every day. So what we do is instead we package big clumps of particles together and say, hey, let's call this a mole. And each mole has this very large number of particles in it. And the one I'm showing you, 6.022 times 10 to the 23rd, has 4 sig figs. But you can get even more precise if you go look it up. The question is, how then do we actually count something if there's so many of them? Because it would take forever to count just one mole. So it's luckily for us, the mass of something is related to how many that we have. And so we can measure mass very accurately. And if we have a relationship then to the mass of a particle to how many particles there are, then we can just use that forever. And so that's what's been established over time. Is on the periodic table, though, when you look for these, when you look at all this information that's given, we first have the atomic number, which is the number of protons. We have the symbol He, in this case, for helium. And then we have this number, which is called, the atomic mass or the atomic weight, depending on who you're talking to. And it's kind of saying that, hey, these heliums on average are going to have a 4.00 AMU, and it's a weighted average. That's all great. But what is an AMU? Well, it turns out that an AMU is the number of grams that you would find if you had a mole of that stuff. So for helium, that means if I give you 1 mole of helium, it's going to have a mass of 4 grams. You put that on a scale, it's going to be 4 grams. So if I give you 2 moles, that's obviously going to be 8 grams. That's the beauty of this. Now that we know this relationship between the mass and the number of moles, then we're going to be in great shape. We can always use this forever. We also have the other relationship that's been established, and that is Avogadro's number. There's a certain number of particles, doesn't matter what kind of particle or thing we're talking about, in a mole of that thing. Fantastic. Well, there's 2 types of masses that we need to keep track of. The atomic mass, which is on the periodic table, and then there's the molecular mass. And that's just something that we compute from the atomic masses of the atoms that make up the molecule. So our formula are never going to have anything but whole numbers, and therefore it's just going to represent how many of each type of atom are in the molecule. So it's really now just a job of putting together how many of each atom we have, multiplying it by its mass, and adding those up for every type of atom in a molecule. Quick example, carbon dioxide is CO2. You can imagine then that there's 1 carbon and 2 oxygens. We have 1 12.01 grams per mole, got that off the periodic table. 2 at 16 grams per mole, got that off the periodic table. If I add all that up, I get 44.01 or 0.1 grams per mole of carbon dioxide. All right, so what we're really going to be doing then is we have this ability now to go between the actual number of particles and the moles of particles, or vice versa. And we do that by realizing that what converts them from one to the other is Avogadro's number. And then we can also go between moles of particles and the mass of particles just by looking at the periodic table and getting the atomic mass or the molecular mass. An important point for you to get right now straight is that the atomic mass and the molecular mass is always the number of things per 1 mole. Doesn't matter what else is written down on a piece of paper or what anyone else says, it's always per 1 mole. Never more than 1, never less than 1, exactly 1 mole. All right, well, let's look at a couple examples. First off, we've got this molecule ethane, C2H6, and we wonder how many moles of this stuff we have if someone was to give us 9.876 times 10 to the 24th molecules. That's a lot of molecules. So you can see why someone wouldn't want to really talk about it in that sense. It's better to get into a size that we're used to. So we do this just like any other conversion. What are we looking for? The number of moles of ethane. What do we know? We know the number of molecules of ethane. We also know there's a conversion between the number of molecules of something and the moles of it. And that's given by Avogadro's number. We cancel out our units, do our multiplication, we find there's 16.4 moles of ethane in 9.876 times 10 to the 24th molecules. Great. Well, that's one type of thing. We can go back and forth, like I said before, between the actual number of particles, which is given here, and the moles of particles, which we found. But we could also do the other thing. We can go from moles to mass, or the other way around from mass to moles. Let's look at the second example. So in this example, we're asked to find the mass, the number of grams, that 16.40 moles of ethane would give us if we were to put it on a scale. So we're looking for the number of grams. We know we've got 16.40 moles of this ethane stuff. And what we know is the periodic table allows us to convert from moles to grams or from grams to moles. All right, so there we go. The periodic table says that ethane is going to have a molecular mass of 30.08 grams per mole, and the moles will cancel out, and voila, we calculate this out, 493.3 grams of ethane. So there you have it, two examples of how we can go back and forth between either the number or the moles or the mass and the moles. Everything goes through the what? The mole.